Hello, good afternoon. Happy Tuesday, everybody. Welcome to our AP Physics 1 review session. My name is Joshua Beck. I'm coming to you from Clayton, North Carolina. I hope you enjoyed the last couple days with Greg. He'll be back again tomorrow, and then I'll be back again the end of the week here. So today we're going to continue our review session. Or our review process. We're going to start by going over yesterday's practice problem. Then we're going to do a real quick review of free fall because we kind of need that to go into our horizontal projectile review. We're going to include some QQT practice today. I know some of you are wondering what exactly does a QQT look like. So we're going to sneak in a little practice there so you can see what that looks like. If we've got some time, we'll show you how projectiles can be mixed in with some other units. And then we'll leave you with a little practice problem for tomorrow. So let's start with a little warm-up. Yesterday, Greg left you with this question. I'll put it up on the screen so you can see it for just a minute. We've got two different vehicles. We have a car on the bottom here, and we have a truck. They're both stopped at the light. Light turns green. Here's the scenario, though. The car was at rest when the light turned green. The truck was already moving. So the truck was approaching the intersection, goes through the intersection right as the light turns green, which I guess means he timed it up quite well. Anyway, so we've got this truck and the car. Now, obviously, the truck is going to jump out to an early lead here because it's already moving. The car, it says, is going to gradually pick up speed. It says it's going to accelerate at a uniform rate. So what we want to do is we want to create a velocity versus time graph, and we want to sketch a line for the car and a line for the truck. And then it tells us we want to indicate any important velocities or time. So switch over here. So we've got a little bit bigger screen to work on. So let's start with the truck. The truck is a little bit easier because at the beginning, when time equals 0, our truck is already moving. Okay, so our truck's going to be right there. I'm just going to pick a velocity somewhere. Now, as time passes, that truck is moving at a constant speed, so its velocity graph is going to look just like this. Okay, so here's our truck. And now, if you look at the question here, it says, use explicit reference to physics principles and equations to explain why you drew the graph the way that you did. Well, let's see. The truck traveled with a constant speed. Is that true? Yes. That was given in the problem. So if it travels with a constant speed, that's going to be a horizontal line. Now, some of you may be wondering, well, wait, shouldn't my line be going up if it's traveling at a constant speed, covering a bigger distance as it goes? Well, this is a velocity time graph. So we're not graphing its location, we're graphing its speed, and its speed is constant. So the equation here, the speed is going to be the initial speed plus acceleration times time. There is no acceleration for the truck, so that speed is just going to be whatever its initial speed is. So I'm going to label that on my graph. It said to label any important V and T values. Now for the car is going to start out with a speed of 0, so it's going to be down here. Now that speed is going to gradually increase. It says that it was going to increase at a uniform rate, so that means that this velocity will increase at a uniform rate. Okay. Now we need to justify that line. Well, it started at rest, so that's why my V equals 0, and it increased at a uniform rate, so that means a constant A. So that means the slope of this line should be constant. Now the equation here would be initial velocity plus acceleration times time. In this case, the initial velocity is 0. So we end up with V equaling A times T. A is a constant value. That's going to be the slope of our line. Now we want to label the time when these things cross. So they cross paths at a distance D. That's where that house was located. So I'm going to label this. Now it's tempting to look at this intersection right here and say, ooh, I bet that's the time where they cross paths. Well, that's where the two lines cross paths. But remember, these lines are showing us the velocity. They're showing us how fast these vehicles are moving. So at that point, right here, at that point, both vehicles are moving at the same speed. Does that mean they're at the same location, though? Well, no, because the truck got off to a head start, and the car's been trying to catch up. Well, at the time when it matches the speed, it still hasn't caught up. At that point, the car is finally going faster than the truck. So now the distance between them will slowly close as it catches up. But this right here is not the time where they cross. That's the time where they both have the same speed. Anything after that, the car is actually traveling faster. So the car is actually covering more ground every second. So the car will be catching up. So how do I figure out the location? Well, you have to remember how we find displacement or distance traveled here from this velocity time graph. In order to do that, we take the area underneath this curve. So if I look at the area underneath the curve for this car, it's this little triangle right here. The area for the truck is this big square. So the truck has covered a larger area, or a larger distance, because we have a larger area right there. So we have to keep moving a little bit. Let's say I go over to here, to this time. Well, the car is still accumulating this area. That's the area underneath the curve, so that represents the distance traveled. The truck during that period is accumulating the same distance because it has the same area. But the car actually has this extra area up here. And that extra area is because ever since we passed this point, the car is moving faster. So it's actually going to cover greater distances. Now this area right here, this little triangle right here, makes up for this little triangle right here, where the car was behind by a little bit in the beginning. And so this is going to be the point where they've both traveled the same distance, because that's the point where both lines have the same area underneath their graphs. Okay. If you have additional questions about this, feel free to reach out to myself or to Greg, and we can help answer these questions. But I want to use this concept of two different motions happening independent of each other to kind of look at projectiles today. So a real quick review: what's necessary to make an object accelerate? We need an unbalanced force. What type of acceleration is needed to speed an object up? Greg looked at this a little bit yesterday. Don't say positive, don't say negative, because those are just directions from a certain person's perspective. You might be watching something from one side of a table and be like, oh, it's moving to the right. That must be positive. Somebody else watching from the other side of the table says, well, it's moving to the left. So does that mean it's negative? Well, it's just a different perspective. So I don't care about positive or negative acceleration. In order for something to speed up, the acceleration just has to be in the same direction as its movement. To slow down, it just needs to be in the opposite direction. Okay, so again, just some quick review. What happens if there's no acceleration? So the truck, for example, there was no acceleration. That means its velocity won't change. What circumstances must be met to consider an object in free fall? Oh, well, this is different. This is something very specific now. We're going to be using this today. In order to be in free fall, we have to have the force of gravity as the only unbalanced force acting on it, which is going to create an acceleration. What is the y velocity at the peak of any free fall? I don't care if I drop it. I don't care if I throw it up. I don't care if I throw it down, throw it at an angle, whatever. What's the y velocity, the vertical velocity at the peak? 0. Always. Has to be. Think about it if it wasn't. If my vertical velocity was anything other than 0, let's say it still had some upward vertical velocity. Well, that means it's still moving up. So has it reached the peak yet? No. What if it's got a downward vertical velocity? Well, that means it's moving down. So it's not at its highest point anymore. So is that the peak? No. Whenever it's at the peak, the y velocity will be 0. Anything other than that means it's still rising or it's already falling and it's not at the peak. So at the peak, the y velocity will be 0. So we're going to use that with our first example problem today. I've got a meter stick set up here, and I'm going to put a tennis ball right about here. Okay, that tennis ball is going to fall 0.92 meters. Okay, so we want to calculate the time that it's going to take to fall. So quick kinematics calculation. I'm going to list my variables, my initial velocity, my final velocity. I could put delta x, but since I'm dealing with vertical here, I'm going to call it delta y, a, and t. So I'm just going to drop this. I'm just going to drop it from that height. So my initial velocity should be 0. The final velocity, when it reaches the ground, I'm not really sure how fast it'll be going when it hits the ground. I do know that my delta y is going to be 0.92 meters. You might say, well, should that be positive? Should that be negative? It really doesn't matter which way I set this up. I've just written it as a positive number. So I've just inadvertently defined down as my positive y direction. That means my acceleration is going to be positive because I've just identified down as my positive direction. So 10 meters per second per second. Again, you may be familiar with using 9.8. It's perfectly acceptable to estimate that as 10 for your AP exam. Time, this is what we're actually looking for. Okay, so I'm going to pick one of my kinematics equations. It'll be written as delta x. I can use delta y. Vy initial. Okay, now my initial y velocity is going to be 0. So this just becomes 1/2 times my y acceleration, which is 10, t squared, and the distance is 0.92. So if I take my calculator here, the 0.5 times 10, that's just going to be 5. So I'm going to take 0.92. I'll divide it by 5. That'll equal t squared. Take the square root of that. And I get a time of 0.43 seconds. So somewhere between 4 and 5 seconds for this thing to fall. Okay, so let's check it out. Here's the setup. I'm going to drop it and it's going to fall. Now, if you look, I've got a timer right here. It's not super clear. I apologize for that, but I've got this timer. Now you can see on this timer, it is at like 39 seconds right now. So I didn't start the timer at 0. Okay, so if I back this up a little bit, we can see that when I let this thing go, I'm going to release this at a time on this timer says 39.5, and then when it hits, boom, hits at 39.92. I'll let you see it one more time. Hit. So the difference in time here is going to be 0.42 seconds, which is exactly what we would expect. Okay, so our free fall calculation works beautifully, which is good. We need it to move into our next step. So what happens if this is launched instead of dropped? The word dropped usually means it's just let go, so it just falls straight down. If something's launched, thrown, then it's going to be more of a projectile scenario where it's going to have some horizontal velocity. All right, so would the time be greater than, less than, or equal if this was launched horizontally? So we've got the one that's going to drop like this, and we know that that time equals 0.42 seconds. And then we're going to take one and we're going to launch it here. What's the time going to be? Well, let's look at our last calculation and let's look at each one of our variables. All right, well, the last calculation we looked at was like this. Well, if we look at each of these variables, if I'm launching it, I'm introducing a horizontal velocity, but my initial y velocity is still 0. My initial y acceleration is still going to be the 10 meters per second per second. So I still have the same y displacement, I still have the same y initial velocity, and I still have the same y acceleration. So my time has to be the same. Okay, so here's the scenario. Let this thing play out. Here this is a horizontal projectile. Okay, you can see it's landing further away. It's got a horizontal component to it. Now, if you look, this thing leaves the table. If you look at the timer right here, start this over. This thing's going to leave the table at about 5.3 seconds. Boom, it's off. And then boom, it lands at about 5.72. So we're going from 5.3 to 5.72. You can see that the time interval is basically the same. It's about 4 to 4.5-ish seconds for this thing to fall. Now, why does this occur? Well, because it's got the same vertical displacement. Okay, so it has the same delta y. It has the same y acceleration. Okay, and it has the same initial y velocity. If I change any of those things, then these aren't going to hit the ground at the same time. So it's got to fall the same vertical distance with the same starting velocity and the same acceleration. Okay, and because those are all the same, this is going to hit the ground at the same exact time. Now, here I'm going to do them simultaneously so you can confirm. Now, does the one on the right have an x velocity? Of course. That's why it moves in the x direction. Okay, so this one has a delta x. All right, play this again. But does that affect the y motion of this, the vertical motion? No. See, what makes these tennis balls fall? What makes them fall is gravity. They're both in free fall. They both have a downward force of gravity acting on them. So that's going to immediately, once that leaves the ramp, it's immediately in free fall. So gravity is going to immediately start to pull it down. And it's going to fall down at a faster and faster speed. That speed will increase by 10 meters per second every second. So both of these are going to accelerate downward and pick up speed the exact same rate. So it doesn't matter that there's this x component. Gravity is still pulling down on it. Gravity doesn't give it a pass. Gravity doesn't say, oh, I see that you're moving. Let me just go ahead and wait a second, and now I'll push. No, it gets pushed the moment that it leaves that ramp. It's in free fall. So both of these are going to fall in unison together. So what do we need to know moving forward? Well, the key to analyzing projectile motion is to keep these x and y variables separate. Does this vertical acceleration change the horizontal speed? Well, no. The vertical acceleration, or the a acceleration, isn't going to affect the x velocity. Or the other way around, the x velocity won't affect the vertical acceleration. So when we look through a projectile problem, step one is going to be to just sort of model that vertical motion as free fall, completely independent of what it's doing horizontally. Then the second step would be to bring that horizontal component into it. Now it's important to remember one of these variables is not direction dependent and can be used to connect them, and that's going to be time. So we could use the vertical information to solve for time, we can use the horizontal information to solve for time, and that time should be the same. So let's set up a real quick problem here. How far from the base of a 10-meter ledge, it's a 10-meter ledge, how far from the base, so I'm going to be looking for this right here, does this projectile land if it's launched horizontally at 5 meters per second? Well, the fact that it's moving at 5 meters per second has no impact on the vertical motion of this. So I'm going to start my calculation with the vertical information. The vertical velocity is going to be 0. Well, it says 5 meters per second. Yeah, that's not vertical. That's the horizontal. So my vertical velocity is going to be 0. Final vertical velocity, don't know it. Displacement, 10 meters. Hey, look, I've just defined down as my positive direction. Can I do that? Sure. As long as I keep it consistent, my acceleration is also down. So that's going to be my acceleration due to gravity. So if I want to solve for my time right here, then I can set this up. My initial y velocity is 0, so I'll just go ahead and include this. This falls 10 meters, 1/2, 10. If I set this up, the 1/2 times 10 gives me 5, so I'll do 10 divided by 5, that equals t squared. So square root of that gives me t, and it's about 1.4 seconds. Now that didn't tell me how far away this thing lands. That's okay, because the entire time that it's falling, it's also moving horizontally. So let's analyze the x motion. The initial x velocity is 5 meters per second. What's the final x velocity? Well, still 5 meters per second, because there's no horizontal acceleration. There's nothing launching it or accelerating it as it flies. Now, a common misconception, people think about what happens while it's being launched, whether it's a spring that's launching it or a ramp or something like that. That part of the problem isn't the projectile part of it. It's not in free fall while it's on the ramp. It's not in free fall while it's being pushed by a spring. It's in free fall. It's a projectile after it leaves that edge. And once it leaves that edge, there's no more horizontal acceleration. So my x acceleration is 0. Okay. So if I want to find my x displacement, I need to use my x velocity. Now, a lot of times people put an x acceleration of 9.8, but horizontally there is no acceleration. So this delta x just simply becomes 5 meters per second times the time that it takes to fall. So this is going to get me 7 meters. That's going to be my range. Now we know that the time is the same for a ball that's dropped and for one that's launched horizontally, because they're both falling the same distance with the same vertical acceleration and the same starting vertical velocity. But what about the final speeds? Well, the final speeds are not going to be the same. See, if I drop one, my final y velocity is going to be my initial y velocity plus any acceleration times time. My initial y velocity is 0. So this is going to be 10 meters per second times 1.4 seconds. This will be 14 meters per second. That's going to be the y velocity for the ball that's dropped. That's when it hits the ground. It's going to hit with a speed of 14 meters per second. There's no x velocity, so this represents its entire velocity. Now, the one that's launched as a projectile, it will have a final y velocity of 14 meters per second as well, because it's also falling. So it's also going to accelerate. So it also ends up with that same final y velocity. But it also has an x velocity of 5 because I launched it and I gave it that. So this thing has some x component and a y component. So the actual velocity is going to be this one right here. So that's going to be the square root of 5 squared plus 14 squared. And this will get us around 15 meters per second. So this one will actually be moving faster. Now, is there a way that I can answer that without calculations? Sure. The one that's dropped, this is the distance it travels. The one that's launched, is that the distance it travels? No, because it landed over here. So this is the distance it traveled, not a straight line. Okay, don't use this and this to then find some straight line across there. Okay, it's not traveling along the hypotenuse, it's traveling along part of a parabola. But this right here is the distance traveled. So the one that's launched, we could say it must travel faster to cover a larger distance in the same amount of time. So now I've justified my answer that this launched projectile is actually going to be moving faster than the one that's just simply dropped. And I didn't even need to do any calculations. I can answer it in my words as well. Okay. So let's set up a little practice problem here. Okay. Practice problem. I've got two different ledges here, H1 and H2. H2 is obviously bigger than H1. They're both being launched with the same initial velocity. Which one's going to go further? I think most people recognize that the one on the right, this second ball number 2, is going to go further. So now that's not the interesting part. Okay, that's great. The AP exam will ask you which one goes further, but then it'll ask you to explain. You need to be able to explain the physics behind it. So how can we explain it? Why does the second one go further? Well, some of you might be saying, well, because it's launched from a higher ledge. Great. But why is it incomplete to just say ball 2 goes further because it's launched from a greater height? You see, if I say that it goes further because it's launched from a greater height, did I bring anything new to this analysis? Did I explain anything, or did I just restate what they already told me? See, if I'm going to explain something, I need to make sure I'm bringing something new to the table. I need to make sure that I'm connecting some dots. Now, yes, the fact that this is launched from a higher height does eventually lead to a greater range, but why? So let's start with what we know, okay? Both of these have the same vertical velocity in the beginning and vertical acceleration, but something's different. Because H2 is greater than H1, ball number 2 will be in the air for a longer time. Okay, great. See, now I'm starting with what I know and I'm connecting the dots, but did I connect it to range yet? Did I explain why it goes further yet? Well, not yet. That's okay. I just need to keep going. Okay, so let's continue. Because they both have the same starting velocity, number 2 can travel farther in that longer time. See, now I've taken the initial setup and I've connected all the dots, getting me from the relationship between height to time. And then I'm using the x velocity and that time to then connect that to the range. Let's try another one. Which of these two projectiles will go further? Okay, I've got the second height here is now equal to H1. I think most of us will recognize that the second one will go further here as well, but we need to explain why. Well, we can see the difference. The difference is that V2 is greater than V1, but that doesn't fully explain why. Okay, I can see that V2 is greater. If I just simply say it goes further because V2 is greater, I'm not getting anywhere. I'm not bringing anything new. I haven't shown that I can connect that relationship between V2 to the actual range. Okay, so what can I do? Well, let's start with what we know. See, in this case, both of these have the same y initial velocity. Well, you say, wait, no, V2 is greater. Yeah, but that's the x component. Both of them still have the same initial y velocity, which is 0. Same y acceleration, that's important. And the same y displacement. So what does that mean? So they will both take the same time to reach the ground. Now I've addressed all the variables that are relevant. If I want to know how long it takes to hit the ground, I need to know what the initial y velocity is, the y acceleration, and the y displacement. So they're both going to take the same time to reach the ground. Have I explained which will go further yet? Well, no, not yet. So keep going. But number 2 travels faster in the x direction. So what does that mean? Well, if it's going to be in the air for the same amount of time, but it's traveling faster, then that means it's going to go further. So it travels faster in the x direction. So it covers a larger delta x in that time. Boom, done. Started with what I knew, connected all the dots. What's the relationship between v and range? Well, it has to include our analysis of time. So we need to show them that time is going to be the same also. Now let's attack this problem from a little bit different perspective. Let's derive an expression for the time to reach the ground. So derive, that's going to be starting with one of our equations and then using variables. So let's start with our equation here that we've been using. Now, under these circumstances, we know a few things. Based on this setup, the y velocity is going to be 0. So I end up with delta y, but I'm going to rewrite that in terms of the variables given. All right, I was given that variable as h. That's going to equal 1/2. The y acceleration, well, this is in free fall. This is the acceleration due to gravity. We've been using 10 meters per second this whole time. So I'm just going to rewrite that in terms of the fundamental constant, g, and then t squared. So this ends up with 2h over g equals t squared. So the square root of that will equal t. Now I've just derived an expression for the time to reach the ground. Okay, it's going to be based on all these vertical components. So I'm done. Now let's derive an expression for the range. The range is a little bit easier, right? Because the range is just going to be based on our x velocity and our time. Now this is the full equation, but the x acceleration is 0. There isn't one. So my delta x, my range, I can just write vx times t. So am I done? I'm close, but it wants it in terms of the given variables. Okay, well, t was not a given variable. So this is a little bit of an issue still. So what do? I'm just going to rewrite this as v, and instead of t, I'm going to write this as the square root of 2h over g. I'm just going to bring this down and plug that in for t. So now I have an expression for delta x. So now I have an expression for my range in terms of all these given variables. So let's attack this same problem, but from a different, with a different method. I'm going to use the expression to explain which one of these is going to go further. Okay, so I'm going to use the expression to explain which goes further. Well, starting on the left, I can see that the second object has a greater height. So looking at my expression, v from here to here, that's the same. H has increased. G is constant, so that's the same. So that stayed the same, same, and then we've got an increase. So this is going to be, if I increase H, then I'm going to increase delta X. I've just now used my equation to explain that. The one on the right, H is equal in both scenarios, G is equal in both scenarios. So this whole term here is equal. That doesn't change, but I've increased this V. So increasing the launch velocity will increase delta X. And I've come up with the same conclusions that I came earlier. Whoops, sorry, that's going to be covering there, I'm sorry. This is basically what a QQT involves. All right, analyzing the same scenario in multiple ways. In part 1, I had you explain it. All right, we talked about in words, we explained why one of these went further than the other. In part 2, it's more of a quantitative analysis. If there were numbers, I may have calculated some numbers. I didn't need to in this case. Okay, I had this equation and I could look at which variables changed, and the ones that changed are going to cause my delta X to change, either increase or decrease. Okay, so a QQT is really just attacking a problem from multiple methods. You may have a qualitative analysis where you're describing what's going on. You may have a quantitative where you're using these mathematical routines. So let's use this equation. Let's continue on in the problem. How could we change H1 so that the range is doubled? Okay, I want you to look at this and take a minute. How could we change H1 so that the range is doubled? Well, we can see our equation. This is our range. That's our delta x. I want to change h1. I want to double. I want x2 to be 2 times whatever x1 is. So my velocity isn't changing, so I can't use that. So the only variable is I need to keep this in the air longer. Remember, this is t. I need to keep this in the air longer. So I need this whole term to be twice as much. If I just simply double h, is that going to do it? No, because if I just double h and then I take the square root of it, I haven't actually changed that time by 2. I've changed it by the square root of 2. So what I really need to do is I really need to use 4 times h1. So then when it goes in here and I take the square root of it, it's actually twice the value. So that would double my range. Let's try another one. What happens to our range if the launch speed was tripled? Well, using my equation, I can just look at which variables are staying the same, which variables are changing. If I triple the launch speed, that doesn't change h, that doesn't change g, but it does triple this. So my new x will just be 3 times whatever my first x was. How about a combination? What happens to the range if the launch speed and the height are both doubled? Happens to the range if the launch speed and the height are both doubled? Well, we've got our relationship here, except now I'm going to start to change some things on this side. So if I double my launch speed, that's going to end up doubling this. And then if I double h, that's inside the square root, so that's going to be multiplied. Oops, that should be here. That's going to be multiplied by this. So my x2 is just simply going to be 2 times the square root of 2, whatever my x1 was. Okay, so once you have this relationship, maybe you had to derive it in the problem, maybe it was given to you, but just look at the different variables and figure out what is changing and what is not changing. Now, if you wanted to run this through your calculator, this is about 2.8 times our initial. Okay, just trying to give you a different approach here. I know a lot of you have probably spent a lot of time calculating projectile problems. Well, what's the speed? What's the time? What's the distance? What's the height? Punching into a bunch of numbers on your calculator. Keep in mind, you really need to be able to analyze these situations conceptually, but also comparatively. So if I change this, will that increase, decrease, stay the same? And sometimes you need to be able to tell me or tell them how much it changed by. Okay, so with projectiles, the time of flight, just to sort of summarize, time of flight is based on these 3 variables. All 3 of these variables. You change one of these, you change the time of flight. Okay, so make sure that you're analyzing all 3 of these variables. This is the one that people often forget. This will be 0 when launched horizontally. The y acceleration will be g throughout the entire flight. Now, range is affected by x velocity and time, keeping in mind that time is actually dependent on all of these, and then the x acceleration, which will be 0. It's probably going to pop up. There we go. Okay. Now, some other ways you may see this on the exam, I went through kind of a couple different steps of an AP style question where you may be analyzing these various projectiles in relation to each other and then changing some things and seeing how that impacts the range. You also might see a projectile problem sort of woven in with another problem. Okay, let's take a look at this scenario. We've got a block of ice that tells me there's going to be negligible friction there. It's going to slide down this ramp and launch off the table. Okay, but now the initial height, and if you look closely, the height is just the starting point on the ramp. It's doubled. What's the new landing point? Whenever you get a problem like this, just be aware that this is really 2 different problems. Over here, we have an energy analysis. And then over here, we have a projectile analysis. Treat them separately. We know that the range of my projectile is going to be based on this. Well, I haven't changed the height of this table. So that means that my time is going to stay the same. So really, if I want to know what happens to my landing point, I really need to know what happens to Vx. So now we can backtrack to the first part of the problem. The first part of this problem is an energy analysis. We're comparing the energy at state 1 to state 2. I'm calling point 1 there, point 2 right there. So we've got this mgh in the beginning, got 1/2 mv squared when it gets to point 2. This is not the end of the problem. This is just when it becomes a projectile. So we can use our energy analysis here. That'll equal v squared, so v is going to equal the square root of this. So if I'm doubling this, if I'm doubling the height, but then it's within the square root, then that tells me that my second velocity is going to be the square root of 2 times whatever my initial velocity is. So when I take this and plug it in right here, that's going to tell me that my range will be the square root of 2 times whatever my initial range is. Okay, the point of showing you this problem is less about the specifics and more about the approach. Don't get overwhelmed just because you have something that turns into a projectile. Make sure you analyze them separately from each other. You've got a projectile, and everything that you know about projectiles applies. Typically, you're looking for some sort of change that affected the projectile. Well, that change may have come from something earlier. In this case, it came from an energy analysis. Do the energy analysis to figure out how V changes, and then analyze your projectile with this new velocity. Sometimes you see this as a collision style problem, right? You might have one block or one cart sitting at the end of this ramp, just waiting. So this is going to come down and it's going to collide. Well, again, this is really just two problems. Don't get overwhelmed. Don't try and do it all at once. This is a collision problem. This is your projectile problem. Okay, so we could use our, well, and actually here you got some energy, an energy analysis here. So in this particular case, once this cart collides, depending on what type of collision it is, that could potentially affect our launch velocity. And our launch velocity is what's going to regulate our projectile motion. So again, I don't want to go through the specifics. I don't even have numbers in here. I don't need them in here. I'm trying to give you an idea of how to approach things, because on your exam, you could see a million different types of questions with all sorts of different scenarios, numbers, etc. I want you to recognize that a projectile problem may come after some sort of an energy analysis, or in this case, now we have a collision. Now, what I do know is if this is an inelastic collision and they stick together, I know that that's going to lower my velocity. That's my launch velocity. Well, that means that's going to change the landing point. It's going to decrease my X value. If I have an elastic collision, well, then I know one is going to collide and the other one's going to take off. If they're the same mass, this will collide, this will take off with the exact same velocity. So my Vx will equal the initial velocity. And so it won't change the projectile at all. It's going to land at the same exact spot. So don't be afraid to analyze the first part of the problem separately and then see, okay, how does that change my launch velocity? And then analyze the projectile problem on its own. There's a third case this may show up. Projectiles and rotational motion. Oh boy, okay. Well, instead of letting this little block of ice slide down the ramp with negligible friction, now we actually have something where friction is noticeable and it's rolling. It's causing this wheel to roll. We talked about this last week. If something's rolling, then some of its energy has to be converted into rotational energy, leaving less energy available for translational. Again, two separate problems. This is the projectile part. The projectile part, that range is going to be determined by these two variables. In all of these, I'm launching them off the same height table, so my time is equal in all these. I'm not changing it. But what happens to my velocity, my launch velocity? Well, if I let this thing slide down, then all of its energy turns into translational kinetic energy. If I let it roll, then some of its energy goes into rotational, meaning less available for translational, which means that I'm decreasing Vx. And if I decrease Vx, then in this case, I'm going to decrease here, and that'll land more like that. This is actually what was taking place in the first example that I showed you. I had a tennis ball actually rolling down. Now, we weren't comparing it to another projectile, but if you could imagine if I took those same two ramps and I let a tennis ball roll down the one, and maybe I had like a little matchbox car that could just scooch down without rotating like this, well, both of them would take the same time to fall once they were projectiles, but the little car would actually go further because most of its energy is translational, so it would actually be launched with a greater horizontal velocity. So it would go further than the tennis ball. Okay, just something to kind of think about. All right. If you have questions about any of that stuff, please reach out to me on Twitter. I'm not going to have any additional time, I don't think, to answer them right now on the live stream. However, I will spend the next 20 or 30 minutes or so checking over Twitter. So if you have questions about anything, if you've already asked them, I will take the next 20, 30 minutes or so once I log off here, and I will dedicate some time to answering some of your questions. So if anything's kind of in the back of your mind, please feel free to reach out to me via Twitter, and I will take a few minutes and try and get all of your questions answered. In the meantime, if you want to take a screenshot of this, this is going to be a practice problem that will get you prepped for tomorrow. So I'm going to let you take a look at this for a moment, let you get prepped for tomorrow with this guy right here. Greg's going to be working with you guys tomorrow. So he's going to start off class with this problem. So if you want to take, 10 or 15 minutes between now and then to give this a shot, he will go over it to start class tomorrow. In the meantime, good luck with your continued review. Please continue reaching out to me with questions. You guys have been asking some awesome questions. Greg and I have both been really grateful for the quality of questions you guys are asking. There's no question that's too mundane or too simple. We'll be glad to help you guys, and I've really enjoyed helping you thus far. So please continue to reach out to us, and we'll continue doing our best to help prep you guys for this upcoming exam. All right, hang in there, be safe, and I'll see you guys in 2 days. Greg will see you tomorrow.